We're going to be talking about electrostatics, meaning that all of our charges will be at rest. So even if there might be forces between them and whatnot, things aren't going to be free to move. And later on, we'll deal with current flowing in circuits and those situations where charge is moving. But for now, we're just going to be dealing with electrostatics. Now, we know that there's a force that exists between charges, and you also know that opposite charges attract, while like charges repel one another. Coulomb's law, and this is why he got the unit named after him, because he came up with this law, quantifies this force. It says that the force, and this is really the magnitude of the force, the electric force, is equal to K, Q1, Q2 over R squared. And this, again, it only gives the magnitude, so technically there are these absolute values here. Most of the time I'm not going to bother writing the absolute values. I'm just going to, plug in the numbers. And what direction this force is pointing is determined by what you know about attraction repulsion. If we have a positive charge here and a positive charge here, we know that the force on this guy is going to be to the right, because it's going to repel. It's going to push away from the positive charge. Likewise, we know the force on this guy is going to be to the left. It's going to repel from the positive charge. If we have a positive and a negative, we know that they're both going to attract toward the middle, so the net force will be to the left on this guy and to the right on this guy. And based on that direction, that's how we assign the SIGN sign to our quantity. This K is a constant. It is 8.99 times 10 to the 9th Newton meters squared per Coulomb. K is actually not something physical. K is related to another constant called epsilon. It's 1 over 4 pi epsilon naught. And epsilon naught is a physical quantity. It is what's called the permittivity of a vacuum, or historically it was known as the permittivity of free space. We'll talk more about epsilon naught sometime later, but just so you know, K does not pertain to anything physical. It's a derived constant from epsilon naught. Now notice this is a kind of a similar format to the Newton's law of gravitation. So it has the same sort of qualitative thing going on here. The force increases with the masses, gravitational. The electric force increases with the charges, and they both decrease with the distance between them squared, and then there's this constant out front. Now notice K is much bigger, and charges tend to be small, masses tend to be big. But let's take a look at something here. Let's look at a proton and electron. Let's consider the gravitational force and the electric force between a proton and an electron in the hydrogen atom. Gravitational force, of course, is G, which is 6.67 times 10 to the minus 11th, times the mass of the proton. And I'm just going to look at this in sort of an order of magnitude estimation. So the gravitational constant is on the order of 10 to the minus 11th. The electron mass is on the order of 10 to the minus 31st. The proton mass is on the order of 10 to the minus 27th. And then the distance between them, the orbital radius of an electron in a hydrogen atom is 5.29 times 10 to the minus 11th meters. So this is over a 10 to the minus 11th. The electric force between them, we've got a 10 to the 9th on K, the charge of each of them is 10 to the minus 19th, and the distance between them is still 10 to the minus 11th. So if we multiply those out, the gravitational force is on the order of 10 to the minus 69th, and the electrical force between them is on the order of 10 to the minus 29th. So we can see this electrical force is much, much bigger, which is why when we get down to an atomic level, gravitational force doesn't really matter at all, because the electrical interactions between other things are so much bigger. You know, this is a 40 orders of magnitude, and that's good. It's important that the electric force is smaller for our matter to work the way it does. But on a larger scale, you know, macroscopic objects generally don't have a net charge, and so then gravitational force acts on them, and it does its thing, because all the electrical forces are pretty much canceling each other out and, you know, just holding an object in place. They don't matter as much on a macroscopic level, but they're very important to how our atoms and whatnot interact at a microscopic level. I just want to take another minute to consider directions of forces, because this is something that's always confusing to people. Let's say we have three charges sitting in a line. Okay, we've got a positive charge, negative charge, positive charge. So we're just going to think about this qualitatively and not worry about the numbers involved at this point. So let's call this charge Q1, Q2, Q3. All right. Now let's consider the force on Q1. Okay, it would be a vector force on Q1. It would be a vector sum of the force on 1 from 2 and the force on 1 from 3. Underlining is one way to denote that something is a vector quantity. I don't know if I've told you guys that before. Anyway, and so we could punch in the numbers and figure this out, but let's just consider direction. The force on 1 from 2, you know, we could plug in, like I said, we could plug in the numbers and get a value for the force, a numerical value for the force, but the direction you have to determine based on your reasoning. This is a positive charge, this is a negative charge. This negative charge is going to pull the positive charge toward it, so F12 is going to be a force to the right. If we look at 1, 3, these are both positive charges, they're going to repel each other, so the force on 1 because of 3 is going to be to the left. So then when we plug this in, we plug this in as a positive number, and then we plug this in as a negative number because it's going in the opposite direction. So that's how we assign our signs to our forces. The force on 2, 1 and 2 are opposite charges, so they're going to attract. The force on 2 because of 1 is going to be to the left. Again, these are also opposite charges, they're going to attract, so the force on 2 because of 3 is to the right. So we would put a minus sign on the force on 2 because of 1. And the force on 3, from 1, they're both positive, so there would be a repulsive force, which is to the left, or to the right, sorry. And then between 2 and 3, there would be an attractive force, which would be to the left. So the force on 3 because of 2 is to the left. So F31 positive, F32 negative. So you need to make sure you're assigning the correct signs. It's also worth noting that Newton's third law is still in effect. So the force on 1 because of 2 is going to be equal and opposite to the force on 2 because of 1. And we can still apply Newton's third law. All of Newton's laws still apply in the case of electrical force. It's just that what you plug in for the force would be this K, Q1, Q2 over R squared. And that could go into Newton's third law.